Just a moment to get ready. All right, great to have you all back. I'm going to be changing it up a little bit this week, and instead of doing the coding that we've been doing the last couple of weeks, or the firmware work, I'm going to be moving on to some basic introductory type hardware, and covering off making an adapter board. And the main reason I wanted to do this was because I find it's something that, one, a lot of people see as quite intimidating and difficult to do, or think is really difficult, but also something that an awful lot of people are getting wrong. And we see, or I see a little bit, a lot of stuff like this, which, you know, whilst a neat enough board, with its wires just soldered on to the back of an OEM connector. And not only is it horrifically ugly, but it's also not very reliable, and those connections will cause problems. So the answer to that is to make a really neat adapter board. And I can give you an example of those. Here's a little one that I made a long time ago for a MX5 or Miata. And here's a slightly more recent one that I've just been tidying off recently. That's also for an MX5 for the same sort of car, but that's adapting, or will adapt to, the drop bear ECU that I've been testing with. And the main difference with this one, if you can see, is that it also has a relay on board. And that's a really good example of what you can do when you are creating a custom adapter board, to add a few things on, as well as just the actual adapter itself. Okay, so those are the main reasons for why I wanted to do it. I'm going to walk through using a piece of software called kicad, which is the tool that I use for creating PCB files. It's a free and open source tool, so you can just go and download it. In my opinion, it is a simply amazingly powerful tool. I love it. It took me a long time to get on the kicad bandwagon, and the main reason for that is because it does have quite a steep learning curve. It is intimidating at first. It has some things in its workflow that really aren't very intuitive, but that's also why I wanted to run a session like this, to just walk through the absolute basics of creating an adapter board. And I'm also going to give away one of the absolute best secrets on the internet as far as how we go about doing these. This might end up being a two-part episode, just depending on how time goes. I'll start off with doing the real basics of an adapter, and if we get time, I'll move on to adding extra things, like I showed doing a relay on the board as well. If we don't get that today, though, I'll make that for the stream next week. All right, so I'll crack on in a minute. As always, if there's any questions that you want to ask, by all means do so in the stream. If there's any jokes you want to crack or anything like that, feel free as well. All right, so this is the main interface for kicad, and the first thing to realize with kicad and with most other PCB design software is that there's at least two interfaces generally. There's one for a schematic, so drawing up what the design is going to look like, and another for laying out the PCB itself. I've just created a completely blank file here. By default, you get two files created, a schematic file and a PCB file within your project directory. We open up the schematic. Again, we see that it is completely blank. The first thing we're going to need, depending on what our setup is an actual connector for our ECU. And this is where a lot of things start to go wrong. To answer the question from Swampy List, have I used fritzing? Yes, I have used fritzing. I started off using fritzing. All the original Speeduino boards were done in fritzing. I now look back and wonder what the hell I was thinking, because I really don't like fritzing anymore. It's slow, it's buggy. It's got a much shallower learning curve, which is why I started with it. There's no question about that. It is certainly easier to pick up, but it is very, very limited and very, very frustrating to use after a little while. Right, once I moved to kicad, I sort of looked back and thought and wondered why I didn't do it earlier. Okay, so the first thing you'll need is a connector. And this is, I think, where a lot of people get stuck, because they assume that they're probably going to need to create a connector from scratch, which is a difficult thing. It's intimidating, particularly if you're new to the whole hardware design and you've never used the software at all before. But the really great news here is that it doesn't have to be that way. And I've just brought up the Speeduino wiki here because there's a page on it that has connector part numbers. This is just my attempt to create a bit of a listing for ECU connector numbers or connector part numbers, because I find that whilst some of these aren't that difficult to get a hold of, the part numbers can be, and there's a nice little cottage industry out there of companies that charge far too much for these connectors, simply because they have the knowledge of what the part numbers happen to be. So this is my little attempt to start getting a bit of a record of what some common connectors are. I'm going to run through creating an MX5 adapter, simply because it's really simple and I've got a pre-made project we can use with it. What I'll show you next, though, is a really magic site called componentsearchengine.com. And this has to be one of the best unknown secrets around in hardware design, I think. Now, a lot of people do know it, obviously. It's not that big a secret. But if you haven't seen it before, it is hands down the greatest resource for finding parts and layouts for different software. So all I'm going to do is I'm going to grab the part number here for the MX5 connector. And that's you'll find this part number anywhere. You can buy it from quite a few places online. And if we search for it here, and I've searched for just about all of the ECU connector part numbers in my list on this search engine, and they're basically all found. And we see here that it's got a part number here for a 4070 hybrid cap, and this is exactly the right part. So if we grab ECAD model, you do have to sign up. You do have to register to be able to get these parts, but it is free registration. Download that. You can see you get a zip file. Inside the zip, you get a representation of that file in virtually every different electronic CAD software that you'd likely want to use. Now in our case we use kicad, so we've got the files here. We've got a couple of different files, and I'll talk about why we need two different files later, but we get a library file and a mod file. These effectively relate to, if you remember, within kicad I talked about having a schematic and having a PCB layout. And that relates to, we have two different parts, one that goes in each. We have a schematic representation and we have a footprint, which represents what the actual physical layout looks like and how the two of them relate. So we need two parts. What I'm going to do is I'm going to grab these two files and copy them. And I'm going to go to my demo directory. Can everyone see that? Is that too small? I can make it a little bit bigger somehow, I'm sure. And I'm just going to create a folder here, and I'm going to call it lib. You can call it anything you want. I just like to call it lib for library. And I'm going to copy those two files into there. Those are the only two files we need, the lib and the mod. There is another file that we may use later on if we want to get fancy, that's within this zip as well. Oh, sorry, we should have copied all of those, but anyway. And this is the 3D file up here, which is the 3D representation. Now, we don't actually need that for our design at all, but if we bring them in, if we use that 3D file, we can actually get a really nice 3D rendering of what our model will look like. And that, if we go back here, is that you can see what the 3D rendering looks like here. And that's what we actually get with that part. And we can show that in KiCad later. All right, so I'll just dump the rest of those files in here. Okay, so if we jump back into KiCad now, we need to tell it two things. We need to tell it where we have some symbol libraries and where we have some footprint libraries. This is not that hard, and this is sort of some of the things that if you do it up front, makes life a lot easier later on. We'll go in here, we're going to add a directory. We're going to select, so it defaults to our project directory here already. We're going to go into our library directory, and we're going to open that library file. And that's all we need for that part, and that will add that part to our library of symbols. And we're going to do the same for a footprint. Okay, and believe it or not, doing that is pretty much all we need to do to get these part numbers in. If I jump back to my schematic now, I can hit A, and this is where using KiCad starts to get a little bit complicated. There's a lot of little shortcuts and a lot of little things that aren't intuitive to use at first. Once you've been using it for a little while, do become more obvious and do just become second nature. But they're not obvious at first. And I am very open about the fact that yes, KiCad has a really steep learning curve, and this sort of stuff doesn't come easy. So to bring up this, all I hit was A to add, but you've got to learn all these little things. I do strongly recommend that it is something that's worth learning, but yeah, it will take you a little while to pick up. Coming from David, KiCad required FreeCAD to do 3D. I presume this is where the optional file came from on the site. Do you mean to make that 3D file, David, or just to use it? So KiCad doesn't need FreeCAD to use a 3D model. It just takes in a pre-made 3D model, regardless of where it's come from, FreeCAD or any other 3D CAD software, and can import it in. And we're going to grab, what was the part number here again? I forget. Part number was 174917. So now that we've added it in, I should be able to go 174917, and there we go. Here is our part. You'll see it's got 48 pins, which relate to the 48 pins on the connector. It is a 48 pin connector, and we can attach things to every one of the pins on it here. The MH1, 2 and 3 here are sort of virtual pins. They represent the mounting holes, so MH mounting hole 1, 2 and 3. all right, now we need something to actually connect these two, so we're going to add something again, and we're going to just grab a generic connector. In this case, we're going to grab a generic 1 row by 12 position connector. So this doesn't represent anything in particular. It's just a general free to use connector, and we can make it just represent holes on our board. So we're going to grab one of these, and in fact we're going to grab 2 of these, and the easy way to copy it is just to put your mouse over the top of that item, hit C, and you'll get a copy of it. A lot of the keycad interface revolves around having your mouse over things and hitting different key combinations, or hitting different key buttons, I should say. So if I want to edit a part, I put my mouse cursor over the top of it, hit E, and I get the edit dialog, which shows me all the details for it. Likewise, if I want to move something, I put my mouse over the top of it, hit M, and I can now move it around. Okay, so we've got 3 parts on our board now. We've got the actual ECU connector itself. We've got 2 generic connectors. Now, by default, this one will have a footprint already defined, which is the footprint that we added. Now, footprint is simply what this part or what this symbol looks like in a physical space, on an actual PCB. Yeah, comment there from Swampy Liz. Oh my god, it can't be so easy to add a new part. It's a little bit complicated with the directory structure and everything, but I absolutely cannot stress just how good this component search engine site is. And it's the URL here, if you can't see it, is componentsearchengine.com. It is amazing, and it has a ridiculous number of parts on it. Just to give you an example here, pick a random connector, and I haven't tested all of these, but let's check. We'll pick something a little bit oddball. 104 pin Skyline RB25 Neo connector, which is a bit of an oddball connector. Let's see if that's there. I should have actually checked this in advance, but let's have a look. There you go, 104 pin Impulse Mate hybrid connector. It's got the footprint for it, it's got a 3D model for it, it's all just there ready to go for us. And I can't tell you how much of a time saver this is. Okay, so what we haven't done though is assign a footprint to these connectors over here. So KiCad doesn't know what these generic connectors should look like on our board. Doesn't know what to do with them. We can connect things up on the schematic, and I'll show you doing that in a moment, but it won't know what to do with those when we come to the physical side of things. So we're going to add a footprint here, and we get the footprint library popping up, which shows us all our footprints down the left hand side. What we want to do here is just select a very generic connector pin. Connector pin? Connector pin header. That one maybe? I can't remember. Oh, there we go. That's what I got. Okay. This is simply saying what the spacing is between the holes is. Now 2.54 mil is a very common one, so that's what we're going to use here. Now we had a 1-row connector with 12 positions in it, so we want to find a pin header that's called pin header 1x12, and you'll see that there's 3 of them here. There's a vertical one, so these are just straight holes in a board, and they're designed to have the vertical style of pin going down. So similar to what you'd get on a board like this, where the pins would stick straight up at 90-degree angles to the board. We can also have horizontal pins, left and right. Those are SMD ones. We can have horizontal ones like that, where you would have 90 degrees. Now I prefer to use these ones for a generic breakout board, simply because it gives a little bit more space around them. You might still end up putting vertical pins in them, and that will work just fine, but this gives a little bit more space on your board. So I'm going to pick one of those. We're going to apply that. Now I'm actually just going to delete this one here, and I'm going to copy this one again, because this is the one that's already got the footprint on it. And if I have a look at that now, we can see that it already has the footprint in place, which is what we want. Now you will notice as well that there's a number of other fields here, data sheet for example, and that you can also add your own fields. put a URL, or anything that you want in here. And this becomes really useful in managing your, in more complex projects, in managing your bill of materials, as we call it, which is your listing of all of the components that are going to go onto your board. Okay, so we've got a connector, we've got two generic headers. Let's have a look at what that looks like on the PCB side. We don't have any connections between them yet. I'll stress that. And this is where some of KiCad's workflow gets a little bit weird and a little bit less intuitive. There's more ways than one to skin a cat with KiCad, and you can do this different ways, but I'm going to show you the way that I use. It might not be the most efficient way, it might not be the best way, and it does change in newer versions of KiCad, but you can still use this method, and it's the method I learned, so it's what I'm going to stick with. We have to create what's called a netlist. Now, a netlist is all of the connections that are on our board. In this case, there's none, but we still have to create a netlist that includes these three components. So we're going to do that. It's going to ask for a file name for it. Just call it demo breakout or whatever your project name is. You don't need to be fancy with it. And it'll ask you to annotate it. You can see in KiCad at the moment, our part number is J question mark here, and J question mark and J question mark. They don't have a component number on the board or a place number. We need to annotate it to do that. And it will be automatic to do that. All we have to do is hit the annotate button, and we've now got J1, J2, and J3. So it automatically gives them numbers for us. And that's all we need to do to create a netlist. We can now go up to Tools and select Open PCB Editor. And we'll get another window here that looks like this. That is completely blank and is probably quite hard to read actually at the moment, but let's turn off the grid at the back just to make things a little bit easier to read. These, by default, the outline comes in this horrible red, which is probably difficult to read. So it probably just looks like a black screen for you at the moment. That's okay. We'll go up now, and in the PCB editor, there's another button with net on it, which is called Load Netlist this time. So we're going to hit that. We're going to browse for the file. We're going to choose the .NET file that we just created. We open that. And it'll give some information about what it found in that file. And it says we're going to add 3 new symbols, J1, J2, and J3. So it found the 3 things that we placed on our schematic, and it knows to put them on the PCB. I'm going to hit update. Close that. Now we've got our 3 things, and we can place them wherever we like here on this board. I'm going to pop them there. And we're going to see that we've got a connector that, again, looks much like what we would expect to see. It's the same connector that you can see on this board here, the grey one. That's exactly the same connector as what we're working with. 48 pins, 3 mounting holes. You can see on the back of this board, 1, 2, 3 mounting holes. So it's exactly what we would expect to see. We're going to rotate that. And again, this is simply a matter of placing our cursor over the top, and in this case pressing R, which rotates it. If we wanted to move it again, we simply put our cursor over the top and hit M, and we can now move it around. So again, not the most intuitive things in the world in terms of what those key combinations are, but once you get them down, they really do come quite naturally. Okay, so we're going to move these. That's J2, so we're going to move him down here. I'm going to move, oh sorry, we should move J3 down here. I'm going to move J2 up here. Okay, so that gives us the basics for our board, or the basic components for our board. We can then start to build up a board around it, and we see over on the right hand side we have layers. Now every board of a PCB has lots of different things going on it. There's the obvious, there's the traces, which are what's called our copper layer, and we have a front and back layer for those, which simply relate to the front of a PC board and the back of a PC board, because we can have traces running on both of those sides. On more complex boards, you can also have layers inside the board. So you can have a 4-layer board where not only do you have a top and bottom, but you have some layers inside the PCB itself. That's far more complex than we need to go into today. But it gives you an idea of what these layers are. And in typical non-user-friendly KiCad style, these aren't always obvious what the names are. If you work around PCBs all the time, these names become obvious. They appear everywhere. But when you're first looking at them, they're really not, they're not clear at all. The main ones that we're going to use, though, are F.cu, B.cu. These are the two copper layers. So these are our traces. F.cu being the front copper layer, B.cu being the back copper layer. We're also going to look at the silk layers, which is what's called silk screening, which is, in this case, if we have a look at this board, the white text and lines that you see on the board itself. That's known as silk screening. And again, we have front silk screening and back silk screening. And we're also going to initially look at the edge cuts layer. Now the edge cuts defines the physical cutout of the board itself. So we're going to select that layer and we're going to do some graphical lines on that layer. And all I'm going to do is draw a really basic box around this. Now, if I'm going too fast or anything, please just let me know. Oh, I don't have my crosshairs on here, but that's all right. You can see that I haven't quite got that line straight. That's fine. We can go in here and move that point. I'm still getting used to all these key shortcuts on Windows, so I'm going through the learning experience as much as anyone here. There we go. Oh, this is not working well for us, is it? All right, well, I'll leave that line for the moment. I'll fix it in a minute when I can figure out all my keys. So there we go, though. We've got a basic board layout, and we've got 3 connectors or 3 interfaces on it. That's our basics. We're going to jump back now to the schematic. And we're going to actually start making some connections between these. Now, I'm not actually going to do it live because it would be boring and tedious. So what I'm going to do is just close these down and open up a completed version of this project. Oops. Okay, so this should look fairly familiar for what we were already doing. We've got our main connector on the left-hand side, and we've got 2 breakouts, or 2 little pin headers of 12 pins each on the right-hand side. What version of KiCad I'm using? I am using 5.1.6, which I believe should be the latest. I would not recommend going anything less than any of the 5.1 versions. Okay, the only thing that you'll see that's different on on this board from the one we're working in is this, the addition of a relay. I've done that for anyone who's familiar with the early MX5s. They don't have fuel pump control by the ECU. There's a little bit of a workaround, a little bit of a hack, but this is, instead of having a normal ground output to control the fuel pump, they need a 12-volt output. So this is a nice little relay. Oh, thank you so much, Unbon. This is a little relay that's simply switching the ground output from the drop ebb ECU to the base of this relay and sending 12-volt out. So what you'll notice is, and this is a personal style thing, but it's how I prefer to do most of my work, there's no lines actually joining the header here on the left with the two pin headers on the right. What we have instead though is a whole lot of little tags, and every tag is connected to a pin via a wire. And what we do is we create these tags over here, or a label. We say place a global label, and we can give it a name, and we'll get a little label that we can move around. We can, just like before, rotate it however we want it, and we can stick it anywhere we want, and we can join it up with a wire, place wire. And if we wanted to say connect that label to pin 7 over here, we just join the two of them like that. If I wanted to put it somewhere on our headers now, all I need to do is either copy that label, right, by again putting our mouse over it and hitting C, or I can simply place another label over here and use the drop down, and it will show me all of the labels that have already been created. So in this case, I'd select test, and I can put it I think all of my pins are actually used up here. They are. But if I wanted to connect it to pin 1, I'll get rid of launch for a minute. I could simply put it down here, select our wire again, and the shortcut here for wire, by the way, is W. I can simply put my cursor over the point on that label, hit W, and I get a wire connection coming out of it, and I can connect it to pin 1. So what this has done is now created a join in KiCad from pin 1M on the ECU connector to pin 1 on the second of our headers. This is exactly the same as if I had have just done this. Get rid of all this. Taken a wire and joined it all the way over here. It's exactly the same, but it's much neater, and it means that we don't have wires crisscrossing everywhere. It works really well, that method, for header connections. When you're actually doing schematics where you're placing things like resistors and capacitors and switches and all those sorts of things, you'll want to use direct wires like that. And I can show a different project at the end for what that will look like. But particularly when you're doing header connections, I find this is by far the easiest method. Okay, so what does this look like? Say I've made all of my connections in my schematic here. I'm going to open up my PCB editor. I'm going to see what this board looks like. So, much as we had before, we've got, let's zoom out a little bit. We've got the header connection for the ECU on the left-hand side, and we've got our general headers on the right. Now we've also got the relay in the middle, but we won't worry too much about that for now, for the moment. what we've got then is a series of connections between them. Now these ones are all complete, but what I can do, or what I should be able to do here, is create a new PCB. In fact, I might just do it this way. What I'm going to do is go through and delete most of these wires. And what you can see is that when I do that, I get these little white lines showing connections between where things need to go. And this is called a rat's nest. When you first load your netlist in from the schematic, which is what we worked through before, you will get these white line connections which tell you where you need to place a trace on the board. It's up to you where those traces can go. Before anyone mentions it, someone's going to say auto router, and there's a tool in most PCB packages or design packages that will do this for you, and that's called the auto router. I don't like it. Most people don't like it. You'll end up with a mess, and you'll end up with something that is a pain to work with. I really suggest strongly doing it by hand and working your way through creating these links by hand. And that's what I'm going to do for a few here. You can see also that I've created labels for each one of the pins. This is fairly straightforward. You can simply, if I edit this J2 header, you can see that I've added a whole heap of fields here. Crank, cam, tacho, blah, 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 so on and so forth. And the layer that those are created on, so layer, is silk layer. And I can change that, should I wish, but what I want is to have these labels that are here appearing on the board, so I know what each of these pins are when I come to interface it with my ECU. Okay, so we're going to select our trace tool, our route tracks tool over here, and we're going to create a connection between the two. And it's really just as simple as clicking that pin and dragging it over. Now, if we do that, that looks fine. The two of them are connected. Our white line went away, which means that it's now a routed connection, and we're fine. When I go to do the next one though, I can't get through. This other trace is now in my way. KiCad will suggest where it can go, which is hideous, but it does give you a connection through. This is where it becomes a little bit of an art in figuring out the best trace routes. So by default, KiCad will give me something like this, but instead I'm going to just trace my mouse this way and get a route that looks like that. Now it's not in my way, and I can lay the second one similarly. If I've already laid a trace and I decide that it's not where I want it, I can drag it. I can drag, oops, this way, and it will keep the connection in those dimensions. And we can do the same on a corner. Oops. Now I'm doing this by selecting the trace that I'm trying to change, be it that spot, and hitting the D key, D for drag. So that makes it fairly easy to move these things around. You'll see in some cases that when I click, it brings up this little menu and say, clarify your selection. It doesn't know which one I want to select, because where I clicked, there were two things. There's the trace, which is the one I want, but there's also this text in the background, which is on the silk layer. And it tells us that's on the silk layer, or this one. Which one do I want? So I'm just going to select that, and it'll give that particular trace. Okay, so The next thing that you might notice is that some of these traces are thicker than others. And the reason for that is that some wires need to have high current. Just as we would when we were running normal wiring in a car, we can have some wires, like sensor wires, that are quite skinny and thin, or we can have power wires that are quite thick to carry a lot of current. And it's the same with traces on a PCB. The ones that are going to carry a little bit of current have to be a bit thicker. We can fairly easily change them though by selecting the trace. Now in this case, I'm putting my mouse over the top of it and I'm hitting the I button. And the I means select the entire length of that trace. If I just put my mouse over it and click, I just get this little part of the trace, and I can make one part thick and one part thin. But in this case, I want the whole thing. So I put my mouse over it, hit I, and then hit E for edit. And it brings me up the properties for this trace. I can change what layer it's on, or I can change, in this case, the track width. 0.25 millimeters at the moment. If we wanted a really big, thick trace, we could say 1 millimeter, and we get a nice big, thick one. In this case, that's far thicker than what we want, but we do want it a little bit. So we're going to make it about 0.5 mil thick. By default, this one was 1/4 mil, and this one we've now changed to 0.5 mil, and you can see it's a little bit thicker. This will affect how you can route your traces, because all of a sudden, if they're much thicker, there's less room for them to be routed around the board. In this case, it's a fairly simple board, so we don't need to worry too much about that. On this, everything's been run already. You can see I've added a few things like some text on the board and a logo, just to make things a bit prettier. How do you know if the thickness is enough? That's a really good question. The answer is, you go online, go to Google, and you simply go trace width calculator. And there's a whole bunch of these out there, if I could spell. They all basically do the same thing. We can have a look at one of them. It doesn't really matter which. Yeah, so same question there. What thickness do you need for different currents or devices? So if we say we want to carry 3 amps of current, now that's a typical high impedance injector might be, let's say 11 ohms. Let me just bring up a good old Windows calculator here. Okay, so if we've got, say, a single 11 ohm injector on a rail, Ohm's law says that the current required will be the voltage divided by the resistance. We need to overestimate our voltage just for a little bit of a safety factor. So in this case, let's say we're running at 15 volts. Our injector resistance was 11 for the sake of example. So we divide that by 11. And we know that the current, in this case, is going to be 1.3 amps maximum. Now this is for when that injector would be fully held open, so 100% duty cycle. In the real world, it's obviously going to be a little bit less than that, which means that the current itself will be less as well, which gives the trace a little bit of time to cool down. Oh, thank you so much for that donation. Always appreciate it. Oh, and for anyone who was interested, by the way, the hoodies and t-shirts and things are now available as well. There's a link on the YouTube description for where you can grab those. Okay, so we know that we need about 1.3 amps. The trick here, though, is that we might have 2 injectors paired on a single line. So we might be drawing 2 injectors instead of 1 injector. It is as simple, if we've got 2 injectors that are the same, of multiplying that by 2. So we get about 2.7 amps. In this case, 3 amps will be enough, but only just. So let's say maybe we would want to go 3.5 amps here. Thickness. This is talking about the thickness of the copper on the PCB itself. So when these PCBs are made, you probably won't be able to see this very well, but what the board is, it's a piece of fiberglass which a layer of copper gets placed on over the top. And then when they make the PCB to your schematic, they cut little bits of that copper out to make the traces. This setting here is for how thick that copper layer is on top of the board. You can get them in various thicknesses. Typically though, it'll be 1 or 2 ounce per foot square. It's a bizarre unit, but that's what we have. If you go onto a PCB site, and I'll show this in a minute if we have enough time, your standard thickness board will be 1, but you can also get 2. If it's 2, you've just doubled the thickness of your traces, which means they can carry twice as much current. In fact, they can carry more than twice as much current. But you will note that when you do that, the board price jumps quite significantly. If you're just creating a cheap board, you want to calculate it with the thickness of that copper layer as 1. And then you can size your traces accordingly so you can get away with using a cheap board rather than having to pay a lot more for a board. And then it gives a couple of settings to say, well, how much temperature rise are we comfortable with? You know, how hot do we let that trace get? And it goes into a little bit more detail than what you probably need. In this case, you're probably happy with it being at 20 is fine. Probably even a bit more would be a problem either. And then you have your results here for how thickness your traces need to be. Now, there's 2 results here, internal layers and external layers in air. This is what I talked about before, where on our PCB we have, on these, a 2-sided PCB, a front and a back. But you can also get more complex PCBs where the layers are internal to the board. We're not worrying about that. We've only got a top and bottom PCB, so we can ignore the whole internal layer section. And we're going to look at this, results for external layers. 43.7 mil. Now, mil is an interesting measurement. I believe it's simply thousandths of an inch, but I don't use it much. We can change this to millimeters because that's what I prefer to use. Now, in this case, it's saying that, wow, we want a 1.1 millimeter wide trace. We can see that if we said we were happy with a 30-degree temperature rise, that drops to 0.86. If we only want 3 amps, it drops again to 0.7. Now, these numbers generally are very conservative. You can push them a little bit more, but it is, for anything that's high current, it is worth doing these checks just to make sure. Okay, so we're going to say 0.7 mil trace for our injectors, just so we're comfortably carrying enough current. So we can go back to our board. For safety's sake, we'll go 0.8, and we get a nice thick trace. It will mean that if we're going to do all our injectors, we're going to make them the same. And what's going to happen is you'll see that now these 2 traces here are really close to one another. Too close, in fact. And we can tell this by using a really fantastic tool up here, which has got a bug design, which is called, or got a bug logo, I should say, and it's called Perform Design Rules Check. And this is what you should always be using before you finalize your board. We're going to click that, and all we need to do is go run DRC in this case, and it'll say refill zones. I'm not going to talk about refilling for the moment, but we're going to get a message here. We're going to say 2 track ends too close, and it's saying that these tracks here are way too close to each other. We need to move them apart. It's okay, that's fine. We can close that back out. And this is really as easy as selecting that wire, for example, and we're going to press D again for drag, and we're going to move it up here. This one we can drag down. Notice now when we're dragging, it won't actually let these wires get too close. Because we've changed the thickness, it will only let them get so close. If I try to get too close, it'll do what it can to push that other wire out of the way. Probably the same in reverse. Yep. See, if I try to go too low, it'll push the other wire out of the way. So we can move those wires, and we run our design rules check again. And we now say it's clean. There's nothing that's too close. We do, however, have unconnected items. And it'll show us that we've got 3 things here that still need to be connected. We've got 2 injector lines, and we've got a coolant line. This is one of the most important and valuable tools that we have. You must be running it before you export your PCBs. It will tell you where you've got problems, because the first time around you will have problems. It's that simple. Okay, so we could go through now and route all these up. I'm not going to do that live because that's pretty boring. The final thing I wanted to run through today, and I realize I'm going pretty quickly on this, but if people are interested, I can easily run another hardware-based session if you want. It's more user-friendly than the old versions of Eagle. Yeah, Eagle's not great either. I mean, Eagle's a fantastic tool, but again, not a particularly obvious interface sometimes. What we need to do is export this file now, or export our design into a file that we can give to a board manufacturer to produce. And the file format that is used for this is called Gerbers. It's a bizarre name, and it consists of a series of files, one file for each of these layers that we talked about over here. Gerbers are an interesting format in that they're not particularly standardized, which can make things a little bit messy. How do I put the Speeduino logo on the board? That's a question I won't get into today because it's not as simple as it should be. You have to create a part and give it a graphical image. Yeah, it's a bit of fiddling around. Yeah, so I won't run over it today. I can show you just putting text in. That's relatively easy. You can simply select our front silkscreen layer. Now I put labels in that are associated with an item. If we just want free text though, we can select the front silkscreen layer. We can select this one here for text, and we can simply go, let's put it over here. Here is text. And we can move it around, we can rotate it, and we can place it down. And what I can show you, of course, is that we can go into the 3D viewer. And we can get a 3D view of what our board looks like. Now, I haven't placed the 3D model for the connector here. We can do that. It's a little bit of messing around, but we can do that. I'll go through exporting the Gerbers first though, because I think it's just a little bit more important. But you can see here how that text that we placed is now hiding there. We've got these traces that we created before that we can see on the board. This is not necessarily the most practical view in the world, but it is pretty nifty, and it's really great for showing your boards off after you've designed them. All right, we're going to export our Gerbers. It's a couple of steps. And again, it's something that I wish was a little bit simpler, but it is what it is. We go to the file menu and we select plot. We tell it where we want the files to go. In this case, just a Gerber subdirectory underneath our breakout. We can just hit plot and that'll give us the files. We also need these drill files. Now the drill files tell the board manufacturer where all the holes in the board go, where they need to actually perform drills. Hit that button. All we need to do is select the Gerbers directory again, and hit generate drill files. Most of these options will default to the right options here in kicad. That wasn't always the case in the past, and you used to get some pretty weird options selected by default. But all of the recent versions of kicad seem to have pretty sane defaults. So you just select generate drill file. I'm not going to do that now simply because I've pulled and deleted a few things out of this board while we've been testing. So I'm just going to close that. We would hit plot there to get the rest of the Gerbers, and it would export everything out. And what we would get is a series of files. So this is the Gerbers directory that I was talking about that look like this. The DRL file is our drill file, and then every one of these refers to or references one of the layers that we talked about up here. So there's the front silk layer, back silk layer, front copper layer, back copper layer, and what we need to do is just grab all of those files, all of those, and put them in a zip file, and that's what I've done here. Simply zip them up. That's what we need. That zip file then is what we need to give to a board manufacturer. So if we were to go to any of the common board houses, JLC PCB for example, they tend to do quite cheap PCBs, and it's worth probably highlighting at this point that 10 years ago this was much more complicated. The software wasn't as good as it is now, and actually getting PCBs manufactured was far more expensive than it is today. Now it's easy. That the competition is fierce, and it is very cheap. The cost for a board is dependent purely on the size of the board typically, and a couple other options such as the thickness of your copper and those sorts of things. What you want to do, if you can at all, is keep your board design smaller than a certain series of pre-made sizes for PCBs. And the most common one that we worry about with small boards like this is 100mm by 100mm. So a 10cm by 10cm board. This design that we've done is well under that, but very specifically it is 100mm wide and no more. It's obviously not it's obviously not that wide. So 100mm long though. The width is obviously shorter than that. So when we go to our PCB manufacturer, they'll say, what's your board size? Just by default leave it as 100 by 100. Ask how many you want, and a lot of these places will do super cheap prototyping deals if you only want 5 or 10 of them. We only have 2 layers, and how thick. Now the thickness here relates to the thickness of the fiberglass on the board itself, not the copper layers. Let's just hit that with the default. And 1.6 here, by the way, is the default thickness, and that will be the cheapest, which in most cases will be fine. Okay, and we get this screen, and virtually every board manufacturer seems to use the same software for this because they all have these same fields. They're a little bit intimidating at first. You know, what's it asking for? Material type, blah, who knows? For the most part, you don't need to worry about it. All we need to do is add our Gerber file, which is the file we just created. We just select our zip file and it'll upload. And we get a nice little picture of it even. Some places do a picture of it for you, some places don't. Most of them will do this. They will automatically detect the dimensions of your board based on the Gerber files. Now mine will, I've obviously missed a millimeter here, and it's 99 by 53 rather than 100, but that's fine. So we have bias resistance of the sensors. Ooh, very different topic. I can certainly talk about that at the end. I'll get through this process first. and then we'll work on it. Rabiel, I can't hear anything. You're the first person to mention. I'm guessing it's the sound working okay for everyone else. Okay, so we want to say there's our design. How many do we want? We probably only want 5 if we're doing a small run here. We only want one different design. This is for if you're trying to squeeze multiple designs onto a single board run. Not anything that we need to worry about. Delivery format, panel by customer is all we need. That's fine. Don't need to worry about any sort of paneling. This is for when you're trying to include multiple versions of it on the same PCB. So in effect, you will cut each board out rather than them doing it. And if you're doing big volume runs, it can be cheaper this way to do it. Not something we need to worry about at all. PCB thickness, we're going to say 1.6 millimeters. It's the default. It's the cheapest. We can pick a color. Green will always be cheapest, but there's lots of different options. We can see that our price for these 5 boards at the moment is the grand total of $5.50, and there's still a part of me that can't believe we can get PCBs made this cheaply. Depending on which manufacturer you go with, changing the color might change the price. No, okay, so with JLC PCB, they don't care. They will let you do different colors for the same price. But it does say, for example, that black will take 2 more days than green. In fact, for any other color than green. White looks kind of cool, but is a real pain to work with in terms of trying to spot traces and things. Black also looks really good when you get them when they're brand new. When you hand solder them, they kind of look a bit crappy because you get the flux and the burning marks everywhere. Other existing Gerber files for various boards? Definitely. All of the Speeduino official boards and everything I release the Gerbers for, and they're all available on GitHub. Including the adapters, although I haven't popped the Gerbers for this particular adapter up yet. I should do that. That's just more me being lazy than anything else. This is where we select our copper weight. This is what we talked about before around the thickness of that copper. They obviously don't do a 2 ounce in black. You notice that option becomes unavailable. But with green, we can select the 2 ounce. Now, if I've $5.50 for these 5 boards so far, if I select the 2 ounce, it jumps to $22.20. You can see that it is quite a bit more expensive to have that thicker copper, which is why I suggest designing your trace thickness around 1 ounce of copper rather than 2 ounce, just to save yourself a whole heap of money. And the rest of it we don't really need to worry about. We can get into testing and all that sort of thing, but for a simple adapter like this, you simply don't need it. And that's it. You save that to cart, it'll calculate your shipping, and shipping can often be 4, 5, 6 more times the price of your actual boards here. These places do tend to charge a lot, but it still works out very cheaply. And then, 2 weeks later, you'll get your boards in the mail, and you can start adding your parts to it. So that's a very, very quick and dirty run through of creating an interfacing board PCB, how to use KiCad for this kind of task, and you can of course use other packages, but KiCad is the one I prefer, and being open source, it's obviously free. Yeah, I guess that's probably all I want to run through. Actually, in fact, I'll go through adding the 3D file here because that's kind of cool. If I can remember how to do it, it's a little bit fiddly. What I'm going to have to do is just go back to our the zip file that we downloaded, wherever it's put it. We're going to grab this file, our STP file. Pop it in there as well. Oh, I might even have it in here. I can't remember. Ah, I do. I already had it in there. Okay. All right, so we add a directory in here. No, I'm sorry, and all I've done here, by the way, is go into the properties for this connector file, and then select the 3D settings tab, and we can see what it looks like in 3D at the moment. In other words, it has no connector, has nothing, just the footprint. Select to add a folder, and we need to find our project file. What was our part number? I gotta remember all this off the top of my head. That one. One 74917. That one. Oh, that hasn't worked. This is always a little bit messy with 3D stuff. That file, of course. Helps if I pick the right file. Okay, and you can sort of see that we've now got the connector. It's there, but it doesn't know, KiCad doesn't immediately know how it needs to orient this. And this is where it gets a little bit messy. We need to start rotating things. So that one needs to be 90 degrees. That one needs to be 180. And then we need to offset it. So we need to come this way a bit. And again, this is not for the, you don't need to do this for your design, by the way. This is just because it kind of looks cool. Okay, so we can see we're starting to get that roughly into the right position here. We can zoom in and have a look. We seem to say okay, there we go. So that's about aligned. Pretty close. And we should now be able to go into our 3D viewer. And look at that. We can see our, all over the place here. We can see our board with a nice pretty 3D connector on it as well. All right, so that's probably about all I really wanted to run through today in terms of doing those designs. Does anyone have any questions or anything that they want to run through? Does anyone want to see more hardware stuff, more complex boards? I can do a run through of what a plug and play board looks like, or one of the V4 boards. I can do a run through of what some of the basic circuits look like. That had sort of been my plan for next week's session, was to do a walkthrough of the V0.4 board and explain what each of the circuits are and how they work. But that was sort of my thinking, but I'm as always more than happy to go in different directions if people want to see different things. Yeah, okay, so people are interested in hardware. That's pretty cool. All right, so I might do a run through, for example, of the V0.4 board next week and see how that goes. Any news on the NOC project? Not at the moment. Not that I can really talk about. I really do need to sink some more time into it. As far as what I'm working on at the moment, I've done some big changes recently in the firmware to free up some memory. And whilst that's not the most sexy sounding thing in the world, it means that I now have a whole bunch more memory to play with. So I'm going to start chucking a whole bunch of extra things in there that we don't have today. You know, a second ignition table, second boost tables, all those sorts of little bits and pieces that we can do all of a sudden with this memory freed up. So I'm really flat out with that code at the moment. So I haven't been looking at the knock stuff too much, I'm afraid. I know people want it. I know I need to get something out there for that. I do understand. So it is coming though. What was the link for the connector supply in terms of where you can buy one of these connectors, or where you get that file? Search for the TNC for the 3.5 or 3.6 or 3.5 adapter, David. Good question. Let me check. I've actually got those up on GitHub. I thought I did. Let's have a look. So TNC adapter, Gerbers. Bam. There you go, David. So on GitHub, if you look at the main Speeduino files, they're under reference, hardware, TNC adapter, and Gerbers. So David was just wondering where the Gerbers for that TNC adapter is. I'll have to make sure that's the latest version. There were a couple of different versions of it, and they were all done in fritzing too, which is seems like a bit of a nightmare to me now. Any thoughts on onboard VR conditioner, Max and NCV1160? Yep, okay. Good question, Lucas. When I originally started doing Speeduino and the board designs for it, a lot of this was about keeping costs down, and it still is. And my thinking was that to keep costs down, not everyone needs a VR conditioner. So I made it a pluggable board that you could drop in. And that works really well. Sorry about that. Someone's streaming some music into my office. On the drop bear boards, it's going to be a built-on board. It'll be built on to the board itself rather than pluggable. And that's simply because that board is I guess, a little bit intended to be a little bit more feature complete than a DIY type thing. As far as which one's better, I really like the Max boards. The Max 9926 is an amazing little chip. I haven't looked that closely at the NCV1124, but my understanding is that it's a similar sort of thinking. The only downside I've ever seen on the Max chips is on the weird Toyota VR setups that they use, where they have two VR sensors that share a single ground. So you have two VR sensors, but only 3 wires. They absolutely do not work with the Max chips, and I imagine they're probably the same with the NCV, because they use what's called adaptive thresholding, and that really messes up when they have shared grounds like that. That's the only downside I've ever seen to the Maxes. Otherwise, they work really, really well. Much better than the old style circuits, in sort of analog circuits, in my opinion. Have you found an easier way to find OEM connector part numbers? It's not easy, no. If you don't have that part number, it can be really difficult to trace, because even if you have the connector, something like that, they don't have the part number on it anywhere. It's something you just have to find. And all I can recommend is that if you do find one, please either add it to the wiki yourself or shoot me a message and I will add it to the wiki, because this is exactly what I'm trying to get a bit of a listing of. There doesn't seem to be anywhere else, or certainly when I started this, there wasn't anywhere else out there for any listings like this. And this is far from complete. Obviously, it's nowhere near complete, but yeah, it's the ones I've found. It's the ones people have told me about. There doesn't seem to be another easy, obvious way to find those part numbers. It's just a lot of trawling around on the internet, unfortunately. Or trawling around on sites like DigiKey and Mouser, where you can actually buy these things, and trying to find trying to find the parts. What you can do is quite often find the family of connectors that it's in. So if you look at the MX5 or the Miatas, all of the connectors, regardless if it's the 48 pin, the 64 pin, or the 72 pin, they're all in the same family of connectors. The same goes for all of the Nissan connectors. They're all this Impol Mate family for Nissan. And what you can quite often do is say, well, I don't know what the actual part number for this connector is, but I know it's got 76 pins, for example. You then go on to DigiKey or Mouser, look up the Impol Mate series of connectors, and then find the 76 pin one. And you can get some part numbers that way. That's the only other guidance I've really got there. Hopefully someone has the part number out there on the internet. Really, that's the biggest hope for this stuff. Any news on the drop bear? Yeah, plenty of news on the drop bear, or plenty going on with it. It's taking up a huge amount of my time in testing at the moment, which is good. I had some testing going on a mate's Commodore here the other day, where we ran it up on V8 sequential, fuel and ignition, and it fired straight away. It was perfect. I mean, the testing couldn't have gone any better than it did. So that's all terrific. I will be moving ahead to a public beta, maybe in about 2 to 3 months' time. I can actually show you what this looks like, what the project looks like, if anyone's interested. Although I haven't configured it on here. Let's just have a look. While that's loading, what else have we got? Have you tested with the A2 operating mode on the Max 9926? It's been so long since I've looked. I've tested a couple of the modes. I can't remember which one A2 is off the top of my head. I can't even remember which one I'm using on the VR conditioners. So Lucas, I can't answer that off the top of my head. It's been too long ago since I looked up the data sheet with all those modes. There's the drop bear board in KiCad, by the way. It's obviously quite a bit more complicated, and this is the Alpha 3. The Alpha 4 that I'm working on is quite a bit different to this now. This had the pluggable VR conditioner, for example, here, whereas the new boards have that all built on. There are a few physical changes down here with this cutout. Just a whole bunch of little stuff, but yeah, that's the drop bear board. And certainly, yeah, if people are interested in a public beta, I'm kind of hoping to have that ready to go in maybe a couple of months. I'll probably have to do one more alpha test first before I'm really comfortable with that, though. Can I add part numbers to your wiki? Message me on preferably Slack, Swampy. If you can jump on the Speeduino Slack channel and message me there. I can either create you an account to do it directly, or if you just want to flick me the part number, I can add it there too. All right. Interesting question from Slater. Does drop bear use the same 5-volt chip as the MX5 PMP, which has had issues? Yes, it does. But we've been doing, or I've been doing an awful lot of investigation into this lately and dissecting of dead boards. And we haven't come across at this stage one single board where the 5-volt regulator, and this is this chip here that you're talking about, has actually been the cause of the fault. Nearly all of them, where the 5-volt rail has died, has been caused by something else. In almost all cases, it's been a short of that 5-volt rail. And the regulator itself has not been the cause in a single one of those boards that I've seen. So we're still trying to figure out what happened there, whether there was some keep out areas, which is the area between components, was not quite big enough, or whether it came down to a simple manufacturing fault in that particular batch, where we found a lot of cases where there were stray solder blobs and things like that, which were causing these shorts. But yeah, it's not a problem with the actual regulator design. It looks more to be either a manufacturing or a user fault where some solder's got somewhere where it shouldn't, or there's been bridges on the board itself. So we're very much looking into that, Slidette. I hope I'm saying that right, by the way. It is a concern that there were far too many of those boards that had problems with that power rail, but the dissection of every one of those dead boards has indicated that the actual circuit design and the 5-volt regulator isn't where the fault is there. It's elsewhere. Yeah, and there's the same comment here around the 9926. It works really well, but yeah, on the Toyota, it's problematic, and a lot of circuits do have problems with those Toyotas. They're just unfortunately difficult. Okay, guys. I'm probably going to end it there for today, I think, unless anyone's got any more questions. It sounds like hardware is going to be another popular one. So next week, if people are interested, I'll do a run through over the V0.4 board, and I'll sort of explain what some of the circuits are there and how we build up a more complex board. But otherwise, we'll end it there for this week. Thanks for coming along. I had a good time doing this one again, and I'll talk to you all next week.